Hello and welcome to Infinite Science.
Before we begin, I want to invite you to slow down, just for a moment. Let the day recede behind you. Let the noise fade. What we are about to explore together doesn't demand your urgency. It asks only for your attention, your curiosity, and perhaps a willingness to feel small in the most beautiful way possible.
Tonight, we're going to talk about galaxies, islands of light scattered across an ocean of darkness. And among them, we're going to find something that challenges even our most generous ideas about size, about scale, about what the universe is capable of creating when given enough time and space and darkness to work with. You already know the Milky Way. It's home. It's vast beyond human comprehension. A spiral of hundreds of billions of stars wheeling slowly through the void, stretching across 100,000 light-years of space. To us, it feels infinite. It feels like everything. But somewhere out there, drifting through the cosmos at a distance so profound that its light has traveled for billions of years to reach us, there exists a galaxy so large that it makes our Milky Way look like a small town next to a sprawling metropolis. A galaxy so vast that when astronomers first measured it, they had to check their calculations again and again, unable to believe what they were seeing.
We won't reveal its name just yet. For now, let it remain a mystery, a presence waiting in the dark, growing larger as we approach it together, step by step, through understanding.
Let's begin with what we know. Let's begin with home. A galaxy is not just a collection of stars. It's a structure, a system, a family bound together by gravity across distances that dwarf anything we experience in our daily lives. It's gas and dust and ancient light. It's stellar nurseries where new suns ignite, and planetary nebulae where old stars exhale their final breaths. It's the framework upon which cosmic history is written, slowly, patiently, over billions of years. The Milky Way is our galaxy. It's a barred spiral, a gorgeous wheel of light with elegant arms that curl outward from a bright central bulge. From edge to edge, it spans approximately 100,000 light-years. To understand what that means, consider this. Light, which travels at 300,000 kilometers every single second, would need 100,000 years to cross from one side of our galaxy to the other. If you could somehow freeze time and measure the Milky Way with a ruler, you would need to lay down about 950 quintillion kilometers. That number is so large it loses meaning. It becomes poetry rather than mathematics. Within this immense structure, somewhere between 200 and 400 billion stars drift and orbit, each one a sun, many of them with their own planets, their own moons, their own quiet corners where, perhaps, other forms of life have emerged and looked up at their own night skies and wondered. Our sun is just one of those stars. We live about 26,000 light-years from the galactic center, out in one of the spiral arms, a region called the Orion Arm or sometimes the Orion Spur. From our vantage point, we see the Milky Way edge on, which is why on dark nights, far from city lights, we can see that luminous band stretching across the sky, the combined glow of billions of stars, all part of our galactic home. The Milky Way has mass too. Enormous mass. Most of it we cannot see. Stars and gas and dust account for some of it, but the majority comes from something invisible, something we call dark matter. It forms a vast halo around the galaxy, holding everything together with its gravity, shaping the orbits of stars, influencing the very structure of the spiral arms. The total mass of the Milky Way, including this dark matter, is estimated to be somewhere around 1.5 trillion times the mass of our Sun. To humanity, the Milky Way feels infinite. It encompasses everything we've ever known, every human who has ever lived, every story ever told, every triumph and tragedy, every moment of love and loss. All of it has happened within this galaxy, on a single planet, orbiting a single star. And yet, for all its grandeur, for all its incomprehensible size and beauty, the Milky Way is not among the largest galaxies in the universe. It's not even close. In the cosmic census of galactic sizes, our home is medium-sized, perhaps even slightly below average. Comfortable, familiar, but modest when measured against the true giants that lurk in the deep fields of space.
This realization doesn't diminish the Milky Way. If anything, it deepens the mystery. Because if our galaxy is this vast, this ancient, this beautiful, and yet still considered modest in size, what must the largest galaxies be like?
What wonders await us when we turn our telescopes toward the true titans of the cosmos? Before we can truly appreciate the largest galaxy, we need to understand scale, not just intellectually, but emotionally. We need to feel it, the way you might feel the ocean when you stand at its edge and realize how far it extends beyond the horizon.
Let's start with something familiar: Earth. Our planet is vast to us. It contains mountains and oceans, cities and forests, deserts and tundras. To walk across it would take months. To sail around it, even with modern vessels, takes weeks. For most of human history, Earth was the entire universe. It was everything. Now, pull back, zoom out. Our planet orbits the Sun, which sits at the center of our solar system. The distance from Earth to the Sun is about 150 million kilometers, a distance we call 1 astronomical unit. Light from the Sun takes about 8 minutes to reach us. Already, we're dealing with scales that challenge intuition. 8 minutes doesn't sound long, but remember, light travels 300,000 kilometers every second. In 8 minutes, it crosses a gulf so wide that no human will likely ever traverse it directly. But the solar system extends far beyond Earth, out past Mars and the asteroid belt, past the giant worlds of Jupiter and Saturn, past Uranus and Neptune, out into the Kuiper belt where Pluto drifts, and even further into the Oort cloud, a vast sphere of icy bodies that marks the true edge of our Sun's gravitational influence. From one side of the solar system to the other, measuring across the Oort cloud, we're looking at nearly 2 light years, 2 years for light to cross. The distances have already become staggering, and we haven't even left our own stellar neighborhood. Now zoom out again. The solar system is just one among billions in the Milky Way. Our nearest stellar neighbor, Proxima Centauri, is about 4.2 light-years away. Between us and that star, there is almost nothing. Just vast expanses of empty space, dark and cold and silent. The stars we see in the night sky, those familiar points of light, are scattered across hundreds and thousands of light-years. The galaxy is not crowded, it's sparse, with tremendous voids between each luminous island. The Milky Way itself, as we've established, spans 100,000 light-years. It's a wheel of light, but it's also mostly empty space, with stars separated by distances that defy comprehension. If you could shrink the Sun down to the size of a grain of sand, the nearest star would still be over 6 kilometers away. The galaxy is not a solid object, it's a pattern, a structure made of gravity and light and time. But even our galaxy is just one among countless others. Pull back further, and the Milky Way begins to look small. It's part of a small collection of galaxies called the Local Group, which includes the Andromeda Galaxy, the Triangulum Galaxy, and several dozen smaller dwarf galaxies. The Local Group spans about 10 million light-years. 10 million years for light to cross from one side to the other. And the Local Group itself is just a tiny neighborhood within a much larger structure called the Virgo supercluster, which contains tens of thousands of galaxies spread across over 100 million light-years of space. And even that supercluster is just one part of an even larger structure called the Laniakea supercluster, which spans 500 million light-years and contains the mass of about 100,000 trillion suns.
These structures, galaxy clusters, superclusters, filaments, and voids, form what astronomers call the cosmic web. It's the largest scale structure in the universe, a vast network of matter and energy stretching across billions of light years, shaped by gravity over cosmic time, with galaxies strung along the filaments like lights on a web, separated by immense voids where almost nothing exists. This is the scale of the universe we inhabit. And within this incomprehensible vastness, scattered across the cosmic web, there are galaxies of every size and shape. Small dwarf galaxies with only a few billion stars, medium spirals like the Milky Way, massive ellipticals containing trillions of stars. And then, at the far end of the spectrum, there are the giants, the true behemoths. Galaxies so large that they seem to defy the very laws that govern cosmic structure. To find them, we need patience, we need powerful telescopes, and we need to be willing to look deeper into space and therefore deeper into time than we've ever looked before. Think of it this way. When you look at a star 10 light years away, you're seeing it as it was 10 years ago. The light you're receiving left that star a decade in the past. When you look at a galaxy a million light years away, you're seeing it as it was a million years ago. And when you look at the most distant objects in the universe, galaxies billions of light years away, you're seeing them as they were billions of years ago, when the universe itself was young. Astronomy is time travel. Every observation is a glimpse into the past. The deeper we look into space, the further back in time we see. This means that studying distant galaxies isn't just about understanding what exists far away. It's about understanding the history of the universe itself, how structures formed and evolved over cosmic time. The light we receive from these distant galaxies has been traveling through space for so long that the universe has changed dramatically during its journey. Galaxies have merged, stars have been born and died, planets have formed. Life may have emerged and gone extinct, all while photons of light have been racing through the void, carrying information about a distant place and time. And every now and then, we point our telescopes in the right direction, collect enough of those photons, analyze them carefully, and discover something extraordinary. Something that changes how we think about the universe. Something like the galaxy we're about to discuss. Astronomy is a science of patience. Unlike laboratory experiments that can be repeated and verified within hours or days, astronomical observations often take years, decades, or even generations to complete. The universe doesn't hurry. It reveals itself slowly, one careful observation at a time. Discovering giant galaxies begins with looking. Powerful telescopes, both on Earth and in space, point toward distant regions of the sky and collect light. Not just visible light, but infrared, ultraviolet, radio waves, X-rays, every wavelength that carries information from across the cosmos. Each wavelength tells a different story. Visible light shows us stars. Infrared reveals dust and hidden star formation. Radio waves map out hydrogen gas. X-rays highlight extreme energies, black holes, and superheated gas. The process begins with surveys. Telescopes systematically scan large regions of the sky, cataloging everything they find: stars, galaxies, nebulae, clusters. These surveys produce enormous datasets containing millions of objects, each one requiring analysis and classification. Computers help with this task, using algorithms to identify likely galaxies, estimate their distances, and flag objects that appear unusual or particularly interesting. The largest galaxies are often found in galaxy clusters, dense regions of space where hundreds or even thousands of galaxies congregate, held together by their mutual gravity. These clusters are cosmic cities, bright beacons in the darkness, easily visible even at vast distances because of the sheer amount of light they emit. At the heart of many of these clusters, there often sits a giant elliptical galaxy, the product of countless mergers and interactions, quietly dominating its surroundings. When astronomers identify a promising galaxy cluster, they request follow-up observations with more powerful instruments. They need to measure the cluster's distance precisely, determine its mass, map the distribution of galaxies within it, and study the properties of individual galaxies, especially the central one. Distance measurement is crucial and challenging. For relatively nearby galaxies, astronomers can use Cepheid variable stars, stars that pulse with a regular period related to their intrinsic brightness. By measuring the period, they can calculate the true brightness, compare it to the apparent brightness, and determine the distance. For more distant galaxies, they use Type A supernovae, exploding stars that all reach approximately the same peak brightness, making them reliable distance indicators. For the most distant galaxies, where individual stars can't be resolved, astronomers rely on redshift, the stretching of light caused by the expansion of the universe. The faster a galaxy is moving away from us due to cosmic expansion, the more its light is shifted toward the red end of the spectrum. By measuring this redshift, astronomers can calculate the galaxy's distance with reasonable accuracy. Once distance is established, astronomers can determine the galaxy's true size. They measure its angular size, how large it appears on the sky, and use geometry to convert that into physical size. A galaxy that appears small on the sky might actually be enormous if it's very far away, while a galaxy that appears large might be relatively small if it's nearby. But galaxies don't have sharp edges. They fade gradually into the darkness, their outer regions containing only faint, scattered stars and diffuse gas. Where does a galaxy end and intergalactic space begin? There's no clear boundary. So astronomers define galactic size using specific criteria, often measuring out to where the surface brightness drops below a certain threshold, or where the density of stars falls to a particular level. This process requires extraordinarily sensitive instruments. The faint outer regions of distant galaxies emit very little light. Detecting them requires long exposure times, sophisticated detectors, careful calibration, and advanced image processing techniques to separate the faint galactic signal from background noise. Then there's the matter of mass. A galaxy's size is impressive, but its mass tells a deeper story. How many stars does it contain? How much gas? How much dark matter? These questions require careful analysis of light curves, spectroscopy to measure how fast stars are moving within the galaxy, gravitational effects on surrounding objects, and sometimes even computer simulations to model the galaxy's structure and evolution. Spectroscopy is particularly valuable. By splitting a galaxy's light into its component wavelengths, astronomers can identify which elements are present, determine the temperature and age of stars, measure velocities through the Doppler effect, and infer the presence of dark matter through gravitational effects that can't be explained by visible matter alone. All of this takes time. A single paper announcing the discovery of a giant galaxy might represent years of observations, thousands of hours of telescope time, collaboration among dozens of researchers across multiple institutions, and careful peer review to ensure the results are accurate and reliable. The discovery of the largest galaxies often happens quietly. A survey telescope captures images of a galaxy cluster. Astronomers notice that the central galaxy appears unusually large or bright. They request follow-up observations with more powerful instruments. Data is collected over months or years. It's analyzed, checked, reanalyzed. Models are constructed. Uncertainties are calculated. Results are compared with previous observations and theoretical predictions. Eventually, a paper is written and submitted for publication. Other astronomers review it, checking the methodology, looking for errors, suggesting improvements. Revisions are made. More data might be collected. Finally, the paper is published and the scientific community becomes aware of the discovery. But even publication isn't the end. Other teams conduct their own observations to verify the results. Different instruments are used. Different analysis techniques are applied. Gradually, a consensus emerges. Yes, this galaxy is extraordinary. Yes, it really is that large. Yes, it challenges some of our previous assumptions about galactic structure and evolution. This is how science works. not through sudden revelations or dramatic announcements, but through patient, careful, methodical observation and analysis. Each discovery builds on previous ones. Each measurement refines our understanding. Each observation adds another piece to the vast puzzle of cosmic structure.
And sometimes, very rarely, astronomers find a galaxy that stands alone at the top, a galaxy so immense that it redefines what we thought possible, a galaxy that forces us to reconsider our models of how these cosmic structures form and evolve over billions of years.
Such a galaxy was found decades ago, though its true size wasn't fully appreciated until more recent observations with more sensitive instruments. It sits at the center of a massive galaxy cluster, billions of light years away, quietly dominating its cosmic neighborhood, a monument to the power of gravity and the patient work of cosmic time. It's time to reveal its name. IC 1101. The name is understated, almost bureaucratic. It comes from the Index Catalog, a systematic survey of celestial objects conducted in the late 19th and early 20th centuries by astronomers John Dreyer and his colleagues. The Index Catalog was an extension of the earlier New General Catalog, compiled to include objects that had been discovered since the original catalog was published. There's no poetry in the designation, no hint of the grandeur it represents, just a catalog number, IC 1101. Object number 1101 in the Index Catalog. But what a number it represents. IC 1101 is, by current measurements, the largest known galaxy in the observable universe. Not just large, not just very large, the largest, the most massive collection of stars and gas and dark matter ever discovered. A cosmic giant that makes even spectacular galaxies look modest by comparison. It sits at the heart of the Abell 2029 galaxy cluster, located in the constellation Serpens, approximately 1 billion light-years from Earth. When we look at IC 1101, we're seeing light that left that galaxy 1 billion years ago, long before the first hominids walked upright on Earth, before complex life had fully diversified across the planet, when the universe itself was about 13% younger than it is today. The distance is important to understand. 1 billion light-years, not 1 billion kilometers, which would already be incomprehensible. Not 1 billion miles, which would be even more vast. 1 billion light-years. Light, traveling at 300,000 kilometers per second, needs 1 billion years to cross the space between IC 1101 and Earth. The photons arriving at our telescopes began their journey before humans existed, before most of the species we see around us had evolved, before the continents had taken their current shapes. When astronomers first began studying IC 1101 in detail, they encountered something that challenged their expectations. The galaxy was bright, certainly, as befitting the central galaxy of a massive cluster. It was clearly large, even from initial observations. But as they measured its extent more carefully, tracing the faint outer regions where starlight gradually faded into darkness, tracking individual stars and globular clusters in its extended halo, they realized they were looking at something unprecedented. IC 1101 is enormous, truly, incomprehensibly enormous. Initial measurements suggested it might span 4 million light-years from edge to edge. 4 million. To put that in perspective, the Milky Way is about 100,000 light-years across. IC 1101 is roughly 40 times wider than our entire galaxy. If you could place the Milky Way at one edge of IC 1101 and begin traveling at the speed of light toward the far side, you would cross the full width of our galaxy, emerge into intergalactic space, cross the width of 39 more Milky Way-sized galaxies, and only then reach the opposite edge of IC 1101. Some later studies, using more sensitive instruments and different measurement techniques, have suggested the galaxy might be even larger, perhaps up to 6 million light-years across, when accounting for the faintest, most extended stellar halo. The exact number varies depending on how one defines the edge of a galaxy, where one draws the line between galaxy and intergalactic space. But by any measure, by any definition, IC 1101 is a titan. There was disbelief at first, which is natural and healthy in science when confronted with something that seems too extreme, too far outside the expected range. Astronomers checked their measurements carefully. They looked for errors in their distance calculations, their photometric analysis, their assumptions about galactic structure. They wondered if perhaps some foreground or background objects were being mistakenly included in the galaxy's boundaries, artificially inflating its apparent size. But the numbers held. Independent observations confirmed the findings. Different teams, using different telescopes and different techniques, arrived at similar conclusions. IC 1101 was real, and it was staggeringly large. Not just larger than the Milky Way, but larger than any other galaxy ever discovered. It occupied a space at the extreme end of the galactic size distribution, a place where few galaxies existed, where the laws governing structure formation were pushed to their limits. Let's spend time with this galaxy. Let's orbit it slowly, taking in its full measure, understanding not just its size, but what that size means, what it tells us about the universe, about time, about the slow and patient processes that build such cosmic monuments over billions of years. Let's explore IC 1101 in detail, examining its structure, its composition, its history, its place in the cosmic web, and what it reveals about the nature of galaxies, dark matter, and the large-scale structure of the universe itself. Imagine, if you can, a sphere of stars and gas and dark matter stretching across 4 to 6 million light-years of space. Imagine that every point of light within that sphere is a star, each one burning with its own particular color and brightness, each one potentially surrounded by planets, moons, asteroids, comets. Imagine that there are not billions of these stars, but trillions. Current estimates suggest IC 1101 contains approximately 100 trillion stars, 100,000 billion, making it one of the most massive galaxies ever discovered. 100 trillion stars. Let that number sit for a moment. Our Sun is one star. It's the center of our solar system, the source of light and warmth that makes life on Earth possible. It's massive, 330,000 times the mass of Earth, containing 99.86% of all the mass in the solar system. And yet, it's just one star among 100 trillion in IC 1101. The Milky Way contains perhaps 400 billion stars. That's already an incomprehensible number, a collection so vast that if you could visit one star every second, it would take you over 12,000 years to visit them all. IC 1101 contains 250 Milky Ways worth of stars, all gathered into a single immense structure, all gravitationally bound together, all orbiting a common center of mass. If you could visit IC 1101, if you could somehow stand in some impossible observation deck, floating in intergalactic space, and look upon this galaxy with your own eyes, you would see a diffuse golden glow spreading across an enormous section of the sky. Not the tight spiral of the Milky Way with its elegant arms, but something broader, smoother, more ethereal. A vast ellipsoid of light, gently fading at the edges, stretching across your field of view like a cosmic cloud. IC 1101 is an elliptical galaxy, which means it lacks the elegant spiral arms we associate with galaxies like our own or Andromeda. Elliptical galaxies are shaped like spheres or footballs, with stars orbiting in random directions rather than in a flat rotating disk. They range in shape from nearly perfect spheres to highly elongated ellipsoids, and IC 1101 falls somewhere in between, slightly flattened, but not dramatically so. This shape tells us something about the galaxy's history. Elliptical galaxies generally form through mergers. When two spiral galaxies collide and merge, their orderly disk structures are disrupted. stars are scattered into random orbits. The resulting galaxy loses its spiral pattern and settles into an ellipsoidal shape. The more mergers a galaxy experiences, the more elliptical it tends to become, as each merger further randomizes stellar orbits. IC 1101 has experienced many mergers, perhaps dozens, perhaps hundreds. Each one added stars, gas, and dark matter to its growing mass. Each one contributed to its current size and structure. The galaxy we see today is the accumulated result of billions of years of galactic cannibalism, the slow consumption of smaller galaxies that wandered too close to its gravitational influence. Elliptical galaxies also generally have much less gas and dust than spirals. Most of their gas was either consumed in star formation long ago, blown out by stellar winds and supernovae, or stripped away during mergers. Without significant gas reservoirs, elliptical galaxies form very few new stars. Their aging populations, cities of red and yellow stars that have been burning for billions of years, galaxies that have largely finished their active star-forming days and now coast quietly through cosmic time, slowly evolving but no longer producing new generations of stars in large numbers. The stars in IC 1101 are old, very old. Most formed many billions of years ago, perhaps 10 or 11 billion years in the past, when the universe itself was young, only a few billion years old, still in the midst of its most active period of star formation and galaxy assembly. Since then, IC 1101 has been slowly accumulating more stars, not by creating them internally, but by consuming other galaxies, pulling them in through gravitational interactions, dismantling them, and adding their stars to its already immense population. The galaxy's color reflects this age. If you could see IC 1101 directly with your eyes, without the aid of telescopes or cameras, it would glow with a soft yellowish or reddish hue, the characteristic color of older stars. The brightest, hottest, bluest stars, the ones that live fast and die young, burning through their nuclear fuel in just a few million years, have long since exhausted their fuel and exploded as supernovae, or collapsed into white dwarfs, neutron stars, or black holes. What remains are cooler, longer-lived stars, red dwarfs that can burn for tens of billions of years, slowly fusing hydrogen in their cores. Sun-like yellow stars in their middle age, steadily working through their fuel supply. Red giants that have exhausted their core hydrogen and are now fusing helium or heavier elements in their extended atmospheres. These stars give IC 1101 its characteristic warm glow, a testament to its ancient age. The sheer scale of IC 1101 creates temporal and spatial effects that are difficult to comprehend. Light moves fast, faster than anything else in the universe, the ultimate speed limit imposed by the laws of physics. And yet even light would need between 4 and 6 million years to cross from one side of this galaxy to the other. 4 to 6 million years. That's longer than hominids have existed on Earth. That's longer than most mammal species survive before going extinct or evolving into something else. If a supernova exploded on one edge of IC 1101 and you were watching from the opposite edge, you wouldn't see it for millions of years. The light would have to travel across the entire galaxy, passing countless stars, traversing vast gulfs of empty space, before finally reaching your location. By the time you saw the explosion, the neutron star or black hole left behind would have cooled, settled, possibly even acquired a companion star, and begun a new phase of evolution. Consider the stars on the outskirts of IC 1101. Those faint, lonely suns drifting through the galaxy's extended halo, millions of light years from the galactic center. They are so far from the core that they would see it not as a bright central bulge, but as a diffuse glow spread across the sky, somewhat like how we see the Milky Way's central regions from our position in the galactic suburbs. The core of IC 1101 would appear to them much as the Milky Way appears to us, a band of light, a concentration of stars, but even more vast, even more luminous, stretching across a significant portion of the sky. And yet, those distant stars are still gravitationally bound to the galaxy, still part of its structure, still orbiting the common center of mass over timescales measured in hundreds of millions or even billions of years. Their orbits are so large, their velocities so relatively slow, that they might complete only a few orbits over the entire lifetime of the universe. A star in IC 1101's outer halo, millions of light years from the center, might take 2 billion years to complete a single orbit. In that time, galaxies merge, stars are born and die, planets form and evolve, and the entire landscape of the local universe changes. The halo itself is one of IC 1101's most remarkable features. All large galaxies have halos, extended regions of sparse stars and dark matter that surround the main galactic body, fading gradually into intergalactic space. But IC 1101's halo is enormous, even by cosmic standards. It extends far beyond the visible galaxy, perhaps doubling or tripling its effective radius, containing additional trillions of stars, scattered so thinly that they're nearly impossible to detect individually from such vast distances. These halo stars are ancient, often captured from smaller galaxies that passed too close and were torn apart by IC 1101's gravity. When a small galaxy falls into IC 1101's gravitational well, tidal forces stretch it, pulling stars away from both ends. These stars don't immediately join the main galaxy. Instead, they form long tidal streams, rivers of stars that orbit IC 1101 for millions or billions of years, slowly dispersing, eventually settling into the halo as individual stars on eccentric orbits. Some of these tidal streams are still visible today, faint traces of ancient galactic meals, evidence of IC 1101's cannibalistic past. They appear as slight overdensities of stars, subtle patterns that require careful analysis to detect. By mapping these streams, astronomers can reconstruct IC 1101's merger history, identifying how many galaxies it has consumed and approximately when those mergers occurred. IC 1101 sits at the gravitational center of the Abell 2029 galaxy cluster, one of the most massive galaxy clusters known in the universe. The cluster contains thousands of galaxies, most of them much smaller than IC 1101, all orbiting within a shared gravitational well that spans tens of millions of light years. The cluster has a total mass of approximately 100,000 trillion times the mass of the Sun, making it one of the most massive structures in the local universe. IC 1101 is the dominant member of this cluster, the gravitational anchor around which all the others move. It's sometimes called a brightest cluster galaxy, or BCG, a designation given to the most massive galaxy in a cluster, typically found near the cluster's center. BCGs are special objects, often much larger than typical galaxies, formed through preferential growth in the dense cluster environment, where galaxy interactions and mergers are common. The cluster environment is crucial to understanding IC 1101. In regions of space where galaxies are spread thinly, growth through mergers is slow. Galaxies might go billions of years without encountering another galaxy. But in a rich cluster like Abell 2029, galaxies are packed more densely, encounters are more frequent, mergers happen more regularly, and the galaxy sitting at the bottom of the cluster's gravitational well, right at the center, is perfectly positioned to capture and consume galaxies that wander too close. Over billions of years, this preferential growth has made IC 1101 into the giant we see today. It's grown fat on smaller galaxies, accumulating their stars, their dark matter, their gas. It's become the dominant gravitational presence in the cluster, shaping the orbits of other galaxies, influencing the distribution of hot gas that fills the space between galaxies, dominating the cluster's appearance in images. The galaxy's mass is equally staggering. While exact measurements are difficult and vary depending on methodology and the assumptions made about dark matter distribution, Estimates place IC 1101's total mass at approximately 100 trillion solar masses, 100,000 billion times the mass of our Sun, though some estimates go as high as several hundred trillion solar masses. Much of this mass is dark matter, the invisible substance that makes up most of the matter in the universe. Dark matter doesn't emit, absorb, or reflect light. It interacts with normal matter only through gravity. We can't see it directly, but we can detect its presence through its gravitational effects on visible matter, on the motion of stars and gas, on the bending of light through gravitational lensing. Every galaxy is embedded in a dark matter halo, a vast sphere of invisible matter that typically extends far beyond the visible stars. These halos contain most of a galaxy's mass, and their gravity is what holds galaxies together, governs their rotation, and allows them to capture and merge with other galaxies. IC 1101's dark matter halo is immense, probably extending 10 million light-years or more from the galaxy's center, containing perhaps 70 to 90% of the galaxy's total mass.
But even considering only the visible matter, stars, gas, dust, stellar remnants, IC 1101 contains many tens of trillions of solar masses. That's an almost incomprehensible amount of matter collected in one place. If you could somehow gather all that matter together into a single object, it would collapse immediately into a black hole so massive that its event horizon would span hundreds of millions of kilometers. Of course, galaxies don't collapse into black holes because their components are in motion, orbiting the common center of mass. This orbital motion provides support against gravitational collapse, just as the orbital motion of Earth provides support against falling into the Sun. The stars in IC 1101 orbit the galactic center at various speeds, depending on their distance, with typical velocities of several hundred kilometers per second. That's fast, roughly 1,000 times faster than a jetliner, but still slow compared to the speed of light, and slow enough that orbits take hundreds of millions or billions of years to complete.
What does all this mass do? It shapes space itself. According to Einstein's general relativity, mass warps space-time, creating the effect we perceive as gravity. The immense mass of IC 1101 creates a deep gravitational well, bending the fabric of space around it, affecting the motion of everything nearby. Smaller galaxies that wander too close are either captured and eventually absorbed, or have their trajectories dramatically altered, sent flying off in new directions.
Even light is affected. The gravity of IC 1101 can bend light rays passing near it, an effect called gravitational lensing. If a more distant galaxy happens to lie almost directly behind IC 1101 from our perspective, its light will be bent as it passes through IC 1101's gravitational field, sometimes creating multiple images or stretching the background galaxy into arcs and rings. This effect allows astronomers to study both IC 1101 itself and more distant objects, whose light is magnified and distorted by IC 1101's mass, turning the galaxy into a natural telescope. At the very heart of IC 1101, like in nearly all large galaxies, there lurks a supermassive black hole. While its exact mass hasn't been measured with precision, it's extremely difficult to measure black hole masses in distant galaxies. It's estimated to be several billion times the mass of the Sun, possibly even tens of billions of solar masses, which would make it one of the most massive black holes ever discovered. This black hole is inactive or only weakly active at present, not consuming significant amounts of matter and therefore not producing the brilliant radiation characteristic of active galactic nuclei, or quasars. But in the past, during the galaxy's more violent youth billions of years ago, when gas was more plentiful and mergers more frequent, this black hole likely fed voraciously on infalling gas and dust, heating the material to millions of degrees, producing intense radiation across the electromagnetic spectrum, shining as a quasar whose light was visible across most of the universe. Quasars are among the most luminous objects in the cosmos, sometimes outshining entire galaxies, despite being powered by regions smaller than our solar system. They represent supermassive black holes in their active phase, gorging on matter, converting gravitational potential energy into light and heat with extraordinary efficiency. IC 1101's central black hole probably spent billions of years in this state before exhausting its food supply and settling into the quiet retirement we observe today. The structure of IC 1101 is smooth and relatively featureless compared to spiral galaxies. There are no dramatic dust lanes cutting across the galactic disk, no obvious star-forming regions glowing with the blue light of young massive stars, no bright emission nebulae marking sites of recent stellar birth. Instead, the galaxy presents a serene, almost uniform glow that gradually fades with distance from the center, brightest at the core, slowly diminishing outward until it becomes indistinguishable from the background sky. This smoothness is characteristic of giant elliptical galaxies that have undergone many mergers. Each merger stirs and redistributes the stars, erasing any pre-existing structure, mixing stellar populations, and creating a more homogenized distribution. It's like stirring cream into coffee. The more you stir, the more uniform the mixture becomes, until you can no longer distinguish separate components. Within IC 1101, there are globular clusters, dense spherical collections of stars, each containing hundreds of thousands or millions of stars, packed into a region only a few light-years across. These globular clusters orbit the galaxy like satellites, tracing out the gravitational field, providing clues about the galaxy's mass distribution and dark matter halo. If you could somehow observe IC 1101 from within, perhaps from a planet orbiting a star somewhere in its mid-regions, a few 100,000 light-years from the core, the night sky would be breathtaking, unlike anything we see from Earth. Depending on your location within the galaxy, you might see the galactic core as a bright yellowish glow occupying a significant fraction of the sky, far more prominent than the Milky Way's core appears to us, casting enough light to read by, even in the middle of the night. In other directions, you'd see countless stars, perhaps far more stars visible to the naked eye than we can see from Earth, even from the darkest locations far from city lights. The sky might never be truly dark. There might be no real night, just a perpetual twilight glow from the combined light of trillions of distant suns. The darkness we associate with the night sky, that deep black punctuated by points of light, might not exist at all in IC 1101's inner regions. And yet, despite all those stars, despite that constant glow, the spaces between stars would still be vast. Even in a galaxy with 100 trillion stars spread across millions of light-years, the average distance between stars would still be measured in light-years. Space would still be mostly empty. A spaceship traveling through IC 1101 would spend most of its time in darkness, crossing vast gulfs of empty space, only occasionally passing close enough to a star to see it as more than a distant point of light. You could still feel alone in IC 1101, gazing out at those distant lights, knowing that each one is unreachably far, separated from you by distances that even light needs years or decades or centuries to cross. The galaxy would be full of light, but also full of emptiness, a paradox of presence and absence, connection and isolation. IC 1101 has been photographed many times by various telescopes over the decades, including observations by the Hubble Space Telescope, ground-based observatories, and infrared space telescopes. In these images, it appears as a large, diffuse, yellowish ellipse, its light distributed smoothly across its extent, gradually fading at the edges. Surrounding it, you can see several smaller galaxies, some of which are satellite galaxies orbiting RC 1101, others which are foreground or background objects at different distances, coincidentally aligned in the same region of sky. The images don't fully convey the galaxy's scale. No single photograph could truly capture the immensity of something that spans millions of light-years, but they offer a glimpse, a sample of what this cosmic giant looks like from our distant vantage point 1 billion light-years away. They show a galaxy that dominates its region of space, that stands out even among the thousands of other galaxies in its cluster, that represents something extreme, something at the far end of what nature can produce through gravitational assembly. The galaxy's discovery and subsequent study represent a triumph of observational astronomy, a testament to human curiosity and technical ingenuity. Finding such an object requires not just powerful instruments, but also the knowledge of where to look, the expertise to conduct systematic surveys, the patience to collect and analyze vast amounts of data, and the ability to interpret that data correctly, distinguishing real signals from noise, accounting for biases and uncertainties, building a coherent picture from thousands or millions of individual measurements. IC1101 didn't announce itself with dramatic fireworks or obvious peculiarities. It didn't send out a signal saying, "I'm the largest galaxy, look at me." It revealed itself gradually, through careful measurement and analysis, as astronomers pieced together its distance, size, mass, and history, comparing it to other galaxies, realizing slowly that they were looking at something unprecedented, something that pushed the boundaries of galactic structure. Every photon of light we receive from IC1101 has been traveling through space for 1 billion years, 1 billion years. When that light began its journey, Earth was in the midst of the Neo-Proterozoic era. The planet was in the grip of a series of severe ice ages, possibly the most extreme in Earth's history, with glaciers extending almost to the equator, the oceans partially frozen. Life existed, but it was simple: single-celled organisms, early multicellular organisms just beginning to experiment with new body plans and ecological strategies. There were no fish yet, no land plants, no animals. No eyes to see the stars, no brains to wonder about them, no intelligence to ask questions about the cosmos. The light left IC1101 and began its long journey through expanding space, through galaxy clusters and cosmic voids, across unimaginable distances, while on Earth, evolution slowly worked, generation after generation, mutation and selection, adaptation and innovation. Over that billion years, Earth transformed. The ice ages ended. The Cambrian explosion occurred, filling the oceans with diverse, complex life. Fish evolved. Plants colonized the land. Insects took flight. Amphibians crawled onto shore. Dinosaurs rose and fell. Mammals diversified. Primates emerged. And finally, after more than 999 million years of that light's journey, humans appeared, developed agriculture, built civilizations, invented writing, developed mathematics and science, built telescopes, and finally, just in the last few decades of that billion-year journey, pointed those telescopes at the right patch of sky and captured that ancient light. That photon, which left IC1101 1 billion years ago, finally found its destination, finally fulfilled its purpose, finally told us its story. And what a story it tells. A story of a galaxy so large it challenges our assumptions. So massive it represents one of the most extreme structures in the known universe. So distant that its light has traveled through the history of complex life on Earth to reach us. Galaxies are not born large. They grow, they evolve. They change over billions of years, shaped by gravity, by chance encounters with other galaxies, by the slow accumulation of gas and dust from intergalactic space, and by the violent processes that transform cosmic structure over time. IC1101 did not spring into existence fully formed, complete with its 100 trillion stars and millions of light-years of extent. Billions of years ago, at a time when the universe was younger and denser, when galaxies were closer together and interactions more common, when the cosmic web was still actively forming its largest structures, what would eventually become IC1101 began as something much smaller. Perhaps it started as a regular large elliptical galaxy, no different from many others scattered throughout the cosmos, containing perhaps a few 100 billion stars, spanning maybe a few 100,000 light-years. Respectable, certainly, but not extraordinary. Just another galaxy among billions, orbiting through the developing cosmic web, slowly converting gas into stars, quietly existing in the young universe.
But it had one crucial advantage, one piece of extraordinary luck that would determine its ultimate fate: location.
It formed near the center of what would become the Abell 2029 galaxy cluster. As the cluster coalesced from the cosmic web over hundreds of millions of years, as hundreds and then thousands of galaxies fell into the same gravitational well, drawn together by their mutual gravity and by the gravity of the dark matter permeating the region, IC 1101's progenitor sat at the deepest point of that well, right at the gravitational center of the developing cluster. It was the gravitational center, the place toward which everything else would eventually drift, the bottom of the potential well, where objects naturally accumulate over cosmic time. This position gave it an enormous advantage in the slow competition for mass that governs galactic evolution in cluster environments.
And drift they did.
Over billions of years, over timescales that dwarf human history, that exceed the entire span of complex life on Earth, smaller galaxies wandered too close. Some passed by at high speed, whipping through the cluster on hyperbolic orbits, their trajectories bent by IC 1101's gravity, but not captured, escaping back into intergalactic space. Others approached more slowly, falling into the cluster on radial orbits, their velocities gradually decreasing due to a process called dynamical friction.
Dynamical friction is a subtle but important effect. When a galaxy moves through the diffuse gas that fills the space between galaxies in a cluster, or through regions of dark matter, or past other galaxies, it creates a gravitational wake behind it, somewhat like a boat moving through water. This wake exerts a drag force on the galaxy, slowly sapping its orbital energy, causing its orbit to decay, spiraling it gradually inward toward the cluster center, where IC 1101 waits. The process is slow, taking hundreds of millions or billions of years, but it's inexorable. A galaxy that enters the cluster on a wide orbit will find that orbit gradually shrinking, each pass through the cluster bringing it closer to the center, until eventually it falls into IC 1101's sphere of influence and can no longer escape. When two galaxies collide, when they come close enough that their mutual gravity begins to significantly affect their structures, something remarkable happens. They don't crash into each other like solid objects, with dramatic explosions and debris flying everywhere. Remember, galaxies are mostly empty space. The stars within them are so far apart that when two galaxies merge, individual stars almost never actually collide. The probability of any two stars hitting each other during a galactic merger is vanishingly small. Instead, their orbits become entangled. Gravity does its work slowly, carefully, patiently. Stars from one galaxy begin to feel the gravitational pull of the other galaxy. Their trajectories change. They're pulled into new orbits. The galaxy's shapes distort, stretched by tidal forces. Long streams and bridges of stars form, connecting the two galaxies, creating spectacular structures that can stretch for hundreds of thousands of light years. If you could watch a galactic merger in fast forward, compressed from its natural timescale of billions of years down to a few minutes, you would see the galaxies approach each other, pass through each other as their stars intermingle, pull back due to their initial momentum, then fall back together again, oscillating several times, each oscillation bringing them closer, their structures becoming more and more disrupted, until finally they merge into a single unified system. This process is called galactic cannibalism, when one galaxy is significantly larger than the other, which is the case for most of IC 1101's growth. The term is apt. The larger galaxy consumes the smaller one, absorbing its mass, adding its stars to its own population, growing larger with each meal. Over hundreds of millions of years, the smaller galaxy is stretched, torn apart by tidal forces, its stars pulled away and scattered into the larger galaxy's halo or incorporated into its main body. Its gas and dust are stripped away, either fed into the central black hole, triggering a burst of activity, or shock-heated and blown out into intergalactic space, or compressed and triggered into a brief period of star formation before being exhausted.
Eventually, the smaller galaxy disappears entirely, its identity erased, its stars now part of a larger whole, indistinguishable from the stars that were already present in IC 1101. The only evidence of its existence might be subtle patterns in IC 1101's stellar distribution, faint tidal streams, slightly different chemical compositions in certain regions, or groups of stars with similar ages and properties suggesting they came from the same progenitor galaxy.
IC 1101 has experienced this process many times over its long history. Dozens of galaxies, perhaps hundreds, have fallen into its gravitational embrace over the past 10 billion years. Each merger added mass, added stars, added gas and dust and dark matter. Each merger made IC 1101 larger, more massive, more dominant within its cluster. Each merger was a step in the slow process that built the cosmic giant we observe today.
Some of these mergers would have been relatively minor, small dwarf galaxies wandering too close, quickly absorbed, barely leaving a trace, adding perhaps a few billion stars to IC 1101's existing population of trillions. These minor mergers happen relatively frequently in rich cluster environments, maybe once every few hundred million years, providing a steady stream of growth for the central galaxy.
Others would have been more dramatic, major mergers with galaxies perhaps comparable in size to the Milky Way or even larger. Imagine a spiral galaxy with its own spiral arms, its own star-forming regions, its own population of hundreds of billions of stars, drifting into IC 1101's influence. At first, the spiral would remain intact, orbiting the giant elliptical, a separate entity, maintaining its structure and identity. But with each pass through IC 1101's gravitational field, tidal forces would pull at it, stretching it, distorting its elegant arms, pulling stars loose from its outer regions. Gas and dust would be stripped away, either fed into IC 1101's core, where it might trigger a burst of star formation or black hole activity, or scattered into intergalactic space, heated to millions of degrees, glowing in X-rays as it falls toward IC 1101's center. Stars would be pulled loose from the spiral galaxy, scattered into long tidal streams that would orbit IC 1101 for millions of years before eventually settling into its halo. The spiral structure would gradually disintegrate, its disk warped and distorted, its arms torn apart, its neat rotation disrupted into chaotic motion. Eventually, over perhaps a billion years, the spiral would lose its structure entirely, its remaining stars and gas mixing with IC 1101's existing population. Its core would merge with IC 1101's core, its central black hole sinking toward IC 1101's center, where it would eventually merge with IC 1101's supermassive black hole in a catastrophic event releasing gravitational waves that would ripple across the universe. What was once an independent galaxy, a separate island of light in the cosmos with its own history and character, would become simply part of IC 1101, indistinguishable from the trillions of other stars already present, its identity absorbed into the larger whole. This process continues today, though more slowly than in the past. The universe is expanding. Galaxy clusters are becoming more isolated from each other, and within clusters, many of the smaller galaxies have already been consumed. But IC 1101 still sits at the center of Abell 2029, still the dominant gravitational presence in the cluster, still capable of capturing and consuming any galaxy that wanders too close in the future. Astronomers can observe galaxies in the cluster today that are on trajectories that will eventually lead them into IC 1101. Over the next few billion years, these galaxies will fall toward the cluster center, Their orbits will decay, and they will be absorbed. IC 1101 will continue to grow, adding to its already enormous mass, extending its already vast halo, becoming even larger than it is today. But there are limits to this growth. The supply of nearby galaxies is not infinite. As IC 1101 consumes the galaxies in its immediate vicinity, it creates a kind of cleared zone around itself, a region where few galaxies remain. New galaxies can fall into the cluster from larger distances, but this process becomes slower as the universe expands and galaxy clusters become more isolated. Eventually, billions of years from now, IC 1101 might reach a maximum size, a point where growth effectively stops because there are no more nearby galaxies to consume, and new galaxies arrive too rarely to contribute significant mass. At that point, IC 1101 will begin the long, slow process of aging, its stars gradually dying, its light slowly fading, settling into the quiet twilight of galactic old age. Dark matter plays a crucial role in all of this, in the formation of IC 1101, in its growth through mergers, in its current structure, and in its gravitational influence on the cluster. We cannot see dark matter directly. It doesn't emit, absorb, or reflect light, doesn't interact with electromagnetic radiation at all. But we can detect its presence through its gravitational effects on visible matter, on the motion of stars and gas, on the bending of light through gravitational lensing. Every galaxy is embedded in a dark matter halo, a vast sphere of invisible matter that extends far beyond the visible stars, typically containing several times as much mass as all the visible matter combined. These halos are not uniform. They're denser toward the center and gradually fade outward, but they extend to enormous distances, far beyond where any significant number of stars are found. IC 1101's dark matter halo is immense, probably extending 10 million light-years or more from the galaxy's center, far larger than the visible galaxy itself. This halo creates a vast gravitational well, a deep dimple in space-time that affects everything nearby, governing the motion of stars within the galaxy, capturing and absorbing smaller galaxies, influencing the distribution of hot gas in the cluster, shaping the large-scale structure of the cluster itself. It's this dark matter halo, even more than the visible stars, that allows IC 1101 to capture and consume other galaxies so effectively. When a small galaxy approaches IC 1101, it's not just feeling the gravity of IC 1101's visible stars, it's feeling the combined gravity of stars and dark matter together, a gravitational pull that extends far into space, reaching out to capture passing galaxies and draw them inward. Understanding dark matter is one of the great challenges of modern astrophysics. We know it exists. The evidence is overwhelming, from galaxy rotation curves to gravitational lensing to the large-scale structure of the universe. We can measure its effects, we can map its distribution, we can calculate how much of it exists, but we don't know what it's made of. Is it composed of exotic particles that rarely interact with normal matter, only through gravity and possibly through weak nuclear forces? Is it some form of modified gravity, a deviation from Einstein's general relativity that mimics the effect of additional matter? Is it something even stranger, something we haven't yet imagined? These questions remain unanswered, representing one of the biggest mysteries in contemporary physics. What's clear is that dark matter is fundamental to the structure of the universe. Without it, galaxies like IC 1101 would not exist. The cosmic web would not exist. Galaxies would not have formed in the early universe, at least not in the way we observe. Structure formation depends crucially on dark matter, on its gravitational influence, on its ability to clump together and create the gravitational wells into which normal matter falls and forms stars and galaxies. The timescales involved in building a galaxy like IC 1101 are almost beyond comprehension. We're talking about processes that unfold over billions of years, over significant fractions of the age of the universe itself.
Entire stellar generations are born, live, and die while a single galaxy merger completes. Mountains rise and erode away on planets. Oceans form and evaporate. Life emerges, evolves, achieves intelligence, builds civilizations, falls into extinction, all while galaxies slowly circle each other, gradually spiraling inward, eventually merging into one. And yet, for all this time, for all this slow, patient growth spanning billions of years, IC 1101 is still not eternal. Nothing in the universe is eternal, not even structures as vast and massive as IC 1101. Billions of years from now, trillions of years in the future, when the universe is vastly older than it is today, IC 1101 will continue to evolve in ways we can only dimly predict.
It will capture more galaxies if any remain nearby, growing larger still, or perhaps reaching some maximum size, beyond which further growth becomes impossible due to the expansion of the universe or the depletion of nearby galaxies. Eventually, trillions of years hence, when the universe has expanded so much that galaxy clusters become isolated from each other, when cosmic expansion has carried distant structures beyond each other's cosmic horizons, when star formation has ceased because all the available gas has been used up or dispersed, IC 1101 will begin to fade. Its stars will age and die, one by one, their light winking out over immense spans of time. The brightest stars will go first, the massive blue giants that burn through their fuel in mere millions of years. Then the sun-like yellow stars, after 10 billion years or so. Then the smaller orange and red stars, which can burn for tens or even hundreds of billions of years. Finally, the smallest red dwarfs, the miserly stars that use their fuel so slowly they might last for trillions of years, longer than the current age of the universe. As each star dies, the galaxy will become darker, dimmer, colder. Eventually, it will be nothing but a vast cloud of stellar remnants, white dwarfs, neutron stars, black holes, orbiting each other in perpetual darkness, a monument to what once was, a fossil of a time when the universe was young and galaxies shone with the light of trillions of stars. But that future is so distant as to be almost meaningless, so far removed from our present moment that it might as well be in a different universe entirely. For now, in this epoch of cosmic history, IC 1101 shines. It dominates its corner of the universe. It stands as a testament to the power of gravity, the inevitability of cosmic evolution, and the magnificent structures that the universe can create when given enough time and space to work, when gravity and dark matter and chance combine to build something extraordinary. Let's return to home for a moment. Let's ground ourselves in the familiar before we venture further into reflection and meaning. Let's compare directly what we know, our Milky Way, with what we've discovered, IC 1101. The Milky Way, our galaxy, our home, is approximately 100,000 light-years across from edge to edge, measuring across the spiral disk. It contains somewhere between 200 and 400 billion stars, with current estimates clustering around 300 billion. Its total mass, including dark matter, is estimated at about 1.5 trillion solar masses. It's a beautiful spiral galaxy, actively forming new stars at a rate of perhaps 1 to 2 solar masses per year, its elegant arms wrapped around a central bar-shaped structure, with a supermassive black hole of about 4 million solar masses sitting at its core. By cosmic standards, the Milky Way is respectable, substantial. It's larger than most galaxies in the universe. The majority of galaxies are small dwarfs, containing only a few billion to a few tens of billions of stars, modest collections compared to our home. The Milky Way is in perhaps the top 20 or 30% of galaxies by size and mass. It's a significant structure, a major galaxy in its local neighborhood. It's home. It's everything we've known, everything our species has experienced, the stage upon which all of human history has played out. Every person who has ever lived, every civilization that has ever risen and fallen, every war and peace, every achievement and tragedy, every moment of beauty and terror. All of it has happened within this galaxy, mostly on a single planet, but all within the Milky Way's boundaries. Now, place it next to IC 1101. Set them side by side, in imagination if not in reality, and compare.
IC 1101 is 40 to 60 times wider than the Milky Way, depending on exactly how you measure its extent and where you draw the boundary between galaxy and intergalactic space. If scaled down both galaxies so that the Milky Way was the size of a coin, say a quarter, IC 1101 would be the size of a large dining table, perhaps 2 meters across. The Milky Way would fit inside IC 1101's boundaries dozens of times over, with room to spare.
You could line up 40 Milky Ways edge to edge and just span the width of IC 1101. You could fit potentially hundreds of Milky Way-sized volumes inside IC 1101's total volume if you packed them together. Though, of course, that's not how galaxies work. IC 1101 is a single, unified structure, not a collection of smaller galaxies, though it was built through the consumption of hundreds of smaller galaxies over billions of years.
In terms of stellar population, IC 1101 contains approximately 100 trillion stars, compared to the Milky Way's 300 billion or so. That's a ratio of roughly 300 to 1. For every star in the Milky Way, IC 1101 has 300 more. If you somehow visited every star in the Milky Way, spending exactly 1 second at each star, it would take you about 9,500 years to complete the journey, longer than recorded human history.
To visit every star in IC 1101 at the same pace would take 3 million years. 3 million years of visiting one star per second without pause, without rest, without stopping. That's longer than humans have existed as a distinct species. That's longer than most species survive before going extinct or evolving into something else.
The mass difference is equally dramatic. IC 1101's total mass is roughly 100 trillion solar masses, compared to the Milky Way's 1.5 trillion. That's a ratio of about 67 to 1, approaching 70 to 1. IC 1101 is not just larger in spatial extent, it's fundamentally more massive, containing more matter, more energy, more gravitational influence, capable of capturing and consuming galaxies that the Milky Way could never hold.
Even the central black holes differ dramatically in size and mass. The Milky Way's supermassive black hole, Sagittarius A star, sitting at the very center of our galaxy, about 26,000 light-years from Earth, has a mass of about 4 million suns. That sounds enormous, and it is, 4 million times the mass of our Sun, concentrated in a region smaller than Mercury's orbit. But IC 1101's central black hole is likely several billion times the mass of the Sun, possibly tens of billions of solar masses, perhaps even approaching 100 billion solar masses, making it a monster even by supermassive black hole standards. That black hole is capable of swallowing entire star systems without leaving a trace, of producing, when active, more energy than entire galaxies, of warping space-time so severely that the very fabric of reality is bent almost to breaking around its event horizon.
But these comparisons, while intellectually satisfying, while numerically precise, don't quite capture the emotional weight of the difference, the felt sense of scale, the gut understanding of what it means for something to be so much larger than something else that already feels infinite. Let me try another approach, using metaphor and imagination to convey what the numbers sometimes obscure.
Imagine you're standing in a small town, population of few thousand people. It's peaceful, familiar, comfortable. You know the streets, the buildings, the people. You can walk from one end to the other in perhaps 20 or 30 minutes. It feels complete, self-contained, like a whole world unto itself. For someone who's lived there all their life, it might feel like everything, like the extent of what matters.
Now, imagine you're suddenly transported to a megacity of 100 million people, a sprawling metropolis covering thousands of square kilometers, its buildings stretching toward the sky, its streets packed with traffic day and night, its lights visible from space, its economy larger than many countries, its population more diverse than many nations, its scale incomprehensible to someone who's only known the small town.
The small town doesn't disappear because the megacity exists. It's still there, still real, still meaningful, still home to the people who live there. It's still beautiful in its own way, still complete, still functioning, still providing everything its residents need. But the megacity forces a recalibration of scale, a recontextualization of size. It demonstrates that what felt enormous can also be small, that what felt all-encompassing can also be modest, that the universe of experience extends far beyond what was previously imagined.
That's the relationship between the Milky Way and IC 1101. That's the emotional reality of the comparison. The Milky Way remains magnificent. It remains our home, our entire universe of lived experience, the container for everything that matters to us directly. It contains wonders beyond counting, nebulae where stars are born, clouds of glowing gas lit by ultraviolet radiation from hot young stars, planetary systems with moons and rings and auroras and geysers, perhaps even other civilizations somewhere among those 300 billion stars, other intelligences looking up at their own skies and wondering if they're alone. Nothing about IC 1101's existence diminishes that. Nothing about the discovery of a larger galaxy makes the Milky Way less wondrous, less beautiful, less important. But it does put it in perspective. It does provide context. It reminds us that our home, for all its grandeur, is one galaxy among trillions in the observable universe. It's one island in an ocean that stretches further than we can easily imagine, deeper than we can readily comprehend. And somewhere in that ocean, there are islands so vast that they make our home look like a small refuge, a modest sanctuary in comparison. This perspective doesn't make us less significant. If anything, it makes existence more precious, more remarkable, more worthy of appreciation. We live in a universe capable of producing structures like IC 1101, galaxies so massive that they seem to violate intuition, that appear almost impossible. And yet we also live in a universe where small rocky planets can harbor life, where consciousness can emerge from the evolution of matter over billions of years, where beings can build telescopes and peer across billions of light years and measure the immeasurable and comprehend the incomprehensible. The Milky Way is small compared to IC 1101. That's simply true. It's an observational fact, a measurement, a comparison. But it's also miraculous, special in ways that size alone can never capture. It's the galaxy that produced us, that sheltered us, that gave us the raw materials and stable conditions necessary for life to flourish over billions of years. It provided a stable gravitational environment, a region of space where planets could form and maintain stable orbits, where water could remain liquid on planetary surfaces, where complex chemistry could develop undisturbed. In all of IC 1101's 100 trillion stars, we don't know if any have produced life, let alone intelligent life capable of contemplating its own existence, building civilizations, developing science, wondering about the cosmos. It's possible, perhaps even likely, given the sheer number of stars and presumably planets, but we have no evidence. The Milky Way has produced at least one example of intelligent life, us. That makes it special, unique as far as we currently know, remarkable in a way that mere size and mass can never convey. Still, the comparison humbles us in the best way. It invites us to hold two truths simultaneously, two realities that might seem contradictory but are actually complementary. We are significant, and we are small. We matter to each other, to our planet, to our species, and we occupy a tiny corner of a galaxy that is itself tiny compared to the largest structures in the universe. Both are true. Both are important. Both deserve recognition. The Milky Way is our home. IC 1101 is a distant giant, impressive and awe-inspiring, but also alien, unreachable, almost incomprehensibly different from our experience. And that's okay. That's more than okay. That's exactly as it should be. The universe is large enough to contain both the familiar and the strange, the comfortable and the extreme, the knowable and the barely imaginable. IC 1101 is more than just an impressive statistic, more than just a number in a catalog, more than just the answer to a trivia question about the largest known galaxy. It's a laboratory for understanding how the universe works, a natural experiment occurring on scales and timescales that humans could never reproduce artificially, a window into the fundamental processes that govern structure formation and evolution across cosmic history. Every massive galaxy tells a story about cosmic evolution, about the interplay between gravity, dark matter, ordinary matter, radiation, and time over billions of years. By studying IC 1101, by measuring its properties, by analyzing its structure and composition, by understanding how it formed and how it continues to evolve, astronomers are learning fundamental truths about how the universe organizes matter on the largest scales. When astronomers first developed models of galaxy formation in the mid-20th century, when they first began to understand how galaxies might have formed from the initially nearly uniform distribution of matter in the early universe, they had limited observational data to work with. They understood the basic principles: gravity pulling matter together, gas collapsing to form stars, galaxies merging and evolving, but the details were murky, uncertain, subject to revision as more data became available. How large could galaxies grow? What set the upper limit on their size? Why did some galaxies remain small while others became massive? How important were mergers versus internal star formation in building galactic mass? How did galaxy size and mass relate to their environment? These questions didn't have clear answers in the early days of galaxy research, and in many ways, they're still being actively investigated today, with each new discovery refining our understanding. IC 1101 challenged some of those early models and confirmed others. Galaxies this large weren't necessarily expected in early simulations. The amount of merging required to build something of IC 1101's scale seemed extreme, possibly too extreme to occur within the age of the universe. Could a galaxy really consume hundreds of smaller galaxies over billions of years and still maintain a stable structure? Could it really grow to such enormous sizes without somehow disrupting itself? Without becoming gravitationally unstable? Without fragmenting or losing coherence? Apparently, yes. IC 1101 exists, stable and massive, a proof by existence that such galaxies are possible, that nature can build structures on scales that theoretical models sometimes struggle to predict. Its existence forced astronomers to refine their understanding of hierarchical galaxy formation, the idea that galaxies grow through a series of mergers, with small galaxies merging to form larger ones, which then merge to form even larger ones, in a cosmic process that continues over billions of years as structure assembles from the bottom up. IC 1101 is likely the product of dozens or hundreds of mergers over its lifetime, each one adding to its mass, each one contributing to its current structure. The galaxy represents an extreme endpoint of hierarchical growth, a galaxy that has been extremely efficient at capturing and consuming its neighbors, that has been in the right location at the right time to maximize its growth over cosmic history. But IC 1101 also raises questions that remain unanswered even today. How much larger can galaxies become? Is there a maximum size beyond which a galaxy becomes unstable or simply runs out of material to consume? IC 1101 sits at the center of a rich galaxy cluster, continuously fed by infalling smaller galaxies that wander too close and are captured by its gravity. But what happens when that supply runs out? When all the nearby galaxies have been consumed? When cosmic expansion has isolated the cluster from new sources of material? Will IC 1101 continue growing, or has it reached some kind of equilibrium, some natural maximum size determined by the physics of galaxy formation and the availability of nearby material. Current observations suggest it's still growing, still consuming smaller galaxies, but at a slower rate than in the past. The universe is older now. Structure formation has slowed. Merger rates have declined. IC 1101 may be approaching its final size, or it may continue growing slowly for many billions of years to come.
Another question concerns the role of environment in determining galactic size. IC 1101 sits at the heart of a massive galaxy cluster, surrounded by thousands of other galaxies, embedded in an environment where galaxy densities are much higher than average. This environment is crucial to its growth. The dense cluster environment provides a steady stream of galaxies to consume, while also allowing IC 1101 to remain at the gravitational center where it can most effectively capture infalling material.
But what about galaxies in less dense regions, in small groups, or in the field between clusters? Could a galaxy like IC 1101 form in isolation, or is the cluster environment essential to building such massive structures? Current evidence strongly suggests that the largest galaxies are almost always found in clusters, specifically at the centers of massive clusters, which supports the idea that environment matters tremendously in determining galactic size. The largest galaxies form where the density of galaxies is highest, where merger rates are greatest, where material is most readily available. IC 1101 also teaches us about the nature of dark matter, that mysterious, invisible substance that makes up most of the matter in the universe, but whose fundamental nature remains unknown. The galaxy's immense dark matter halo is essential to its structure and growth, providing the gravitational scaffolding that holds the galaxy together and allows it to capture and consume other galaxies so effectively.
Without dark matter, the visible stars and gas would not have enough gravity to hold the galaxy together at such enormous sizes. The galaxy would fly apart, its stars escaping into intergalactic space, its structure dissolving. But the dark matter provides additional gravitational binding, creating a deep potential well that keeps everything contained, that allows the galaxy to maintain its integrity despite its vast size.
The distribution of dark matter within and around IC 1101 provides clues about how dark matter behaves on galactic scales. By studying the motion of stars and gas, by analyzing gravitational lensing effects, by modeling the galaxy's structure, astronomers can infer the distribution of dark matter and compare it to theoretical predictions. This information feeds into broader efforts to understand what dark matter actually is, what particles or phenomena account for this invisible mass that dominates the universe's matter content. There's also the question of future discoveries. The possibility that IC 1101 might not remain the largest known galaxy forever. IC 1101 is the largest known galaxy, but known is an important qualifier, a reminder that our knowledge is limited, that we've surveyed only a fraction of the universe in detail. The observable universe is vast, containing perhaps 2 trillion galaxies, spread across 93 billion light-years of space. We've surveyed only a tiny fraction of them in detail, measured the sizes of only a relative handful, characterized thoroughly only those that are nearby or particularly bright or otherwise distinctive. It's entirely possible, perhaps even likely, that somewhere out there in the vast expanse of the cosmos, even larger galaxies exist, waiting to be discovered, sitting at the centers of yet more massive clusters in regions of space we haven't yet surveyed carefully. As telescopes become more powerful, as survey techniques improve, as our ability to measure faint, distant objects increases, we may find galaxies that dwarf even IC 1101, that push the boundaries of galactic size even further. Or we may confirm that IC 1101 truly represents some kind of upper limit, a maximum size beyond which galaxies cannot grow due to fundamental physical constraints, due to limitations on structure formation imposed by dark energy, cosmic expansion, or the finite age of the universe. Either discovery would be significant. Either would teach us something profound about how the universe works, about the limits of structure formation, about the processes that govern cosmic evolution. IC1101 also connects to broader questions about cosmic structure, about the large-scale organization of matter in the universe. Galaxies don't exist in isolation. They're part of clusters, which are part of superclusters, which are part of the cosmic web, that vast network of filaments and voids that represents the largest scale structure in the universe. Understanding the largest galaxies helps us understand the largest structures, helps us trace how matter organized itself over cosmic history, how the nearly uniform distribution of matter in the early universe evolved into the complex web we see today. How does matter organize itself on cosmic scales? What role does dark matter play in structure formation? How has structure evolved over the 13.8 billion years since the Big Bang? How will it continue to evolve in the future as cosmic expansion accelerates and structures become increasingly isolated from each other? These questions are fundamental to cosmology, to our understanding of the universe as a whole, and studying galaxies like IC1101 provides crucial data for answering them.
These are not abstract questions divorced from practical concerns. They touch on fundamental aspects of reality, the nature of matter, energy, space, and time. They probe the laws of physics that govern the universe, test our theories of gravity and cosmology, challenge our understanding of how the universe began and how it will end. By studying IC1101, astronomers are probing the very fabric of reality, testing Einstein's general relativity on cosmic scales, refining models of dark matter and dark energy, pushing the boundaries of human knowledge about the universe we inhabit.
And there's something deeply human about that endeavor, something that connects to our fundamental nature as curious, questioning beings. We're a species that looks up at the night sky and asks why. We're not content with simply existing, with accepting the world as given. We want to understand. We want to know where we came from, how we got here, where we're going, what surrounds us, what lies beyond the horizon. IC1101, for all its alien vastness, for all its incomprehensible scale, is part of that quest. It's a destination for human curiosity, a puzzle to be solved, a mystery to be unraveled. Every photon we collect from IC1101 is a message from the universe, encoded with information about distance, composition, age, motion, structure. We decode those messages carefully, patiently, translating light into knowledge, observation into understanding. It's painstaking work, requiring expertise in physics, mathematics, astronomy, computer science, requiring patience and dedication and collaboration across institutions, nations, and generations. But the rewards are immeasurable. Each new understanding expands our perspective, deepens our appreciation for the cosmos, and reminds us that we're part of something larger than ourselves, something ancient and vast and wonderful.
There's a particular feeling that comes from contemplating IC1101, from sitting with the knowledge of its existence and trying to comprehend what it means. It's a feeling that's difficult to put into words, but instantly recognizable once experienced, once you've allowed yourself to truly consider the scale and implications. It's a mixture of awe and humility, wonder and smallness, curiosity and peace. It's the feeling of realizing that you're part of a universe far larger and stranger than you previously imagined, and that this realization, rather than being terrifying or diminishing, is somehow deeply comforting, even liberating.
For most of human history, spanning hundreds of thousands of years of our existence as a species, we believed we were at the center of everything. This wasn't arrogance exactly. It was simply the natural conclusion drawn from direct observation and experience. Earth was the center of the universe, the foundation upon which everything else rested. The sun, moon, planets, and stars revolved around us, moving through the sky in patterns that, while complex, clearly centered on our position. Humans were the pinnacle of creation, the reason for existence. the audience for which the cosmic drama was performed. The universe existed for us, with us at its center, both physically and metaphysically. This view was comfortable, reassuring. It made us significant. It gave us purpose. It placed us at the heart of meaning itself.
But science, slowly and methodically over the past 5 centuries, has dismantled that comfortable centrality, piece by piece. Copernicus showed that Earth orbits the Sun, not the other way around, removing us from the center of the solar system. Galileo revealed that the Moon and planets are worlds in their own right, not perfect crystalline spheres attached to celestial spheres, each with its own features and presumably its own physical processes.
Hubble demonstrated that the Milky Way is just one galaxy among countless others, that the fuzzy nebulae astronomers had been observing were actually distant galaxies, island universes in their own right, and that the universe is expanding, carrying galaxies away from each other at ever-increasing speeds. Each discovery pushed us further from the center, made us smaller, less special, less obviously significant in the cosmic scheme.
And yet, and this is the paradox, the beautiful contradiction, the more we discover about the universe's vastness, the more we understand about cosmic scale and our small place within it, the more remarkable our existence becomes. We're not significant because we are at the center. That was never the right criterion for significance. We're significant because we exist at all, because consciousness exists, because meaning exists. In a universe containing galaxies like IC 1101, with its 100 trillion stars spread across millions of light years, with its incomprehensible mass and ancient age, there's also a small blue planet orbiting an ordinary yellow star in a medium-sized galaxy where life emerged from chemistry, where simple molecules became complex, where metabolism developed, where reproduction and evolution began their long work, eventually producing beings capable of contemplating galaxies billions of light years away. That's extraordinary. That's profound. That's a form of significance that doesn't depend on being central or large or dominant. It's a significance based on existence itself, on awareness, on the universe becoming conscious of itself through us. The universe doesn't need us. IC 1101 would exist whether we observed it or not. Galaxies would continue merging. Stars would continue forming and dying. The cosmic web would continue its slow evolution across billions of years, all without any awareness of humanity, all without caring whether we exist. The universe is not here for us. It wasn't created with us in mind. It doesn't have a purpose that includes us in any essential way.
But we're here for the universe, in a sense. We're here in the universe, as part of the universe. We're the part of the universe that has become conscious of itself, that can observe and measure and understand. We're made of the same atoms that make up stars and planets and galaxies, carbon and oxygen and nitrogen and iron, forged in the hearts of stars or in the violent collisions of neutron stars, scattered into space by supernovae, eventually collecting into new planets where they became part of living things.
We are, quite literally, made of stardust. You are made of stardust. Every atom in your body was forged in a star or created in the Big Bang. You're not separate from the universe, observing it from outside. You are the universe, experiencing itself. A local concentration of matter and energy that has achieved sufficient complexity to become aware, to think, to wonder. IC 1101 reminds us of this connection. When you look at images of that vast elliptical galaxy glowing softly against the darkness, you're seeing light that traveled for 1 billion years to reach you. Photons that left IC 1101 when Earth was in the Neo-Proterozoic era, long before complex life existed, long before eyes or brains or consciousness have journeyed across the cosmos to finally enter your eye or strike your telescope's detector, or be recorded by your computer screen. That light connects you to IC 1101 across time and space, creates a relationship between you and that distant galaxy, establishes communication of a sort. You're not just observing it from some detached position. You're in communication with it, receiving its ancient message, interpreting its light, understanding something about its nature and history. The photons that left IC 1101 a billion years ago have fulfilled their purpose by reaching you, by conveying information, by allowing understanding.
There's a peace in accepting our smallness, a comfort in acknowledging our place in the cosmic order. Modern life, particularly in developed societies, often encourages us to think of ourselves as central, as all-important. Our problems feel enormous. Our anxieties feel overwhelming. Our concerns seem to fill the entire universe. We're told to think big, to make our mark, to be significant, to matter.
But step outside on a clear night, far from city lights. Look up at the stars, those ancient points of light. Remember that you're standing on a small planet, the third rock from a medium-sized star, orbiting through a galaxy of hundreds of billions of stars, which is itself one galaxy among trillions, in a universe containing structures like IC 1101, galaxies so vast they make our home look tiny. And suddenly, everything shifts. The perspective changes. The scale recalibrates.
Your problems don't disappear. They're still real, still important to you and to those who care about you. Your anxieties remain. Your concerns persist. But they're also contextualized, placed within a much larger tapestry, a cosmic perspective that spans billions of years and trillions of galaxies. You're one thread in a vast weaving that stretches back to the Big Bang and extends across structures so large that light needs millions of years to cross them. This perspective doesn't diminish human experience, it enriches it. It allows us to hold our immediate concerns while also maintaining awareness of the bigger picture. It invites us to care deeply about our own lives, our families, our communities, our planet, while also recognizing that the universe is vast, ancient, and filled with wonders beyond our immediate experience or comprehension. It creates a kind of balance, a way of being simultaneously engaged with our daily lives and aware of cosmic context. We can worry about paying rent while also marveling at the fact that we're conscious beings made of stardust, living on a planet orbiting a star in a galaxy that's tiny compared to IC 1101. Both scales matter. Both perspectives have value. There is a word in philosophy and aesthetics called the sublime, the experience of confronting something so vast, so powerful, so far beyond human scale that it produces a complex mixture of awe, fear, and pleasure. The sublime is what you feel standing at the edge of the Grand Canyon, hearing thunder rumble. And it's what you feel contemplating IC 1101, trying to wrap your mind around its scale, imagining its 100 trillion stars spread across millions of light years, visualizing the billions of years of galactic cannibalism that built it, considering that the light you're seeing left that galaxy a billion years ago. It's the feeling of your own limits being revealed, of realizing that you're small in the face of something greater, and finding that realization not diminishing, but elevating, not depressing, but exhilarating.
IC 1101 is sublime. It's so large that it defeats easy comprehension. We can speak its dimensions, 4 to 6 million light-years across, 100 trillion stars, 100 trillion solar masses. But those numbers don't really convey the experience of its vastness. They're just words, just symbols, just attempts to capture something that exists beyond language. The true experience comes from sitting with those numbers, turning them over in your mind, trying to imagine what they mean, trying to feel the scale, and eventually arriving at a place where language fails, and all that remains is wonder, pure and unmediated.
And in that wonder, there's a kind of spiritual experience, even for those who don't consider themselves spiritual in any traditional sense. Wonder is a fundamental human response to beauty and mystery, to encountering something that exceeds our ability to fully comprehend. It's what we feel when confronted with profound questions,
with experiences that touch something deep within us, with moments that remind us that existence itself is strange and beautiful and worthy of appreciation.
IC1101 offers us that experience. It's a gateway to wonder, a portal to awe, a reminder that the universe is far stranger and more magnificent than our daily lives suggest. It's an invitation to step outside our human perspective, to imagine timescales of billions of years, to contemplate distances that light itself needs millions of years to cross, to consider structures so massive that they contain hundreds of Milky Ways worth of stars, to expand our sense of what's possible and real.
And perhaps most importantly, IC1101 reminds us that discovery is ongoing, that we haven't figured everything out, that the universe still holds mysteries. We've learned so much about the cosmos over the past century: the expansion of the universe, the Big Bang, dark matter, dark energy, black holes, exoplanets, gravitational waves. But we've only scratched the surface. There are still questions to answer, mysteries to solve, wonders to discover.
The universe is not a finished book. It's a story still being written, a mystery still unfolding. And we're fortunate enough to be living during a chapter when humanity has developed the tools to read that story in ever greater detail, to probe deeper into space and time, to measure phenomena that our ancestors couldn't have imagined, to understand the cosmos in ways that were impossible just generations ago.
We don't know what future discoveries await. Perhaps we'll find galaxies even larger than IC1101, pushing the boundaries of galactic size even further. Perhaps we'll discover that IC1101 represents some kind of maximum, a fundamental limit imposed by the laws of physics or the age of the universe. Perhaps we'll find evidence of life in some of those 100 trillion star systems, other worlds with their own biospheres, perhaps even other civilizations looking up at their own skies and wondering. Perhaps we'll develop new theories that explain the universe in ways we can't currently imagine, that revolutionize our understanding as completely as relativity and quantum mechanics revolutionized physics in the 20th century. Perhaps we'll find answers to the deep questions. What is dark matter? What is dark energy? How did the universe begin? How will it end? Are there other universes beyond our own? What we do know, what we can say with confidence, is that the universe rewards curiosity. Every time we've looked more carefully, we found something unexpected, something that challenged our assumptions and expanded our knowledge. Every time we've built a more powerful telescope, we've seen deeper into space and time, discovered new phenomena, observed the universe in new ways. Every time we've asked a question sincerely and pursued it rigorously, the universe has answered, even if the answer leads to more questions. IC1101 is one of those answers, and like all good answers, it opens up new questions, new avenues of investigation, new wonders to pursue. What is the largest possible galaxy? How many galaxies like IC1101 exist in the observable universe? What happens inside such massive structures over cosmic time? How do they affect the space around them, the evolution of their galaxy clusters, the large-scale structure of the universe? What can they teach us about the nature of dark matter, the evolution of galaxies, the limits of structure formation? These questions will occupy astronomers for years to come, perhaps decades, perhaps generations. And the search for their answers will produce new discoveries, new insights, new wonders to contemplate, new experiences of awe and humility and connection. The story of IC1101 is not finished. It's still unfolding, one observation at a time, one calculation at a time, one wint of human curiosity at a time, one photon of ancient light at a time. Let's return now to where we began, to Earth, to home, to this moment. You're here, perhaps in your room or on your commute, maybe at home or at work, looking at a screen or listening through headphones, experiencing these words, thinking about IC1101 and cosmic scale, and what it all means. And it's okay if you feel a little overwhelmed.
It's okay if the numbers don't fully make sense, if the distances feel abstract, if you can't quite grasp the full magnitude of 100 trillion stars spread across millions of light years, if the timescales of billions of years seem impossibly long. No one can fully grasp it, not really. Our brains didn't evolve to comprehend galactic superclusters or billion-year timescales. They evolved to navigate forests and savannas, to recognize faces and track animals and find food and avoid predators, to manage social relationships and raise children and survive in environments that spanned at most hundreds of kilometers and at most decades of time. They didn't evolve to comprehend the cosmos, to understand structures that span millions of light years, to imagine timescales that dwarf all of human history.
We're doing our best with cognitive tools that weren't designed for cosmic scales, and the fact that we can understand as much as we do, that we can measure distances of billions of light years and estimate masses of trillions of solar masses, and reconstruct the merger histories of galaxies, is itself remarkable. It's a testament to human ingenuity, to our ability to extend our senses through instruments, to extend our reasoning through mathematics, to extend our understanding through careful observation and logical inference. But here's what you can grasp, what anyone can grasp, regardless of their mathematical background or scientific training. The universe is vast. It's older than we can easily imagine, older than most numbers we encounter in daily life. It's filled with structures of stunning complexity and beauty, from the smallest subatomic particles to the largest galaxy superclusters. And somewhere within that vastness, on a small rocky planet orbiting an ordinary star in a medium-sized galaxy, life emerged from chemistry. Simple molecules became complex, metabolism developed, reproduction began. Evolution did its slow, patient work over billions of years. Life diversified, became more complex, colonized new environments, developed new capabilities. Eventually, after billions of years of evolution, life became conscious, became aware of itself, developed the ability to ask questions and seek answers. And that consciousness developed curiosity, that fundamental drive to understand, to know, to explore. And that curiosity led to science, to systematic observation and experimentation, to mathematics and logic and careful reasoning. And through science, we built telescopes and developed theories and made measurements. And through those tools and methods, we discovered IC 1101. That chain of events, from the Big Bang to the formation of galaxies, to the emergence of life, to the development of intelligence, to the birth of science, to the discovery of the largest known galaxy, is a story of the universe becoming aware of itself. We're not separate observers watching from outside, detached from what we're observing. We're participants, integral parts of the story. We're the universe experiencing its own grandeur, matter organized in such a way that it can observe other matter, consciousness arising from unconscious processes to contemplate the whole. IC 1101 existed long before we discovered it. It formed billions of years ago, grew through countless mergers over cosmic time, sat at the center of its galaxy cluster, dominating its neighborhood, all without any awareness that, a billion light years away, on a small planet, beings would eventually evolve who could detect its light and measure its properties. And it will continue existing long after humanity is gone, long after our sun has exhausted its fuel and died, long after Earth has been reduced to debris. In that sense, our observation of it is cosmically insignificant, a brief moment in an ancient galaxy's life. But in another sense, it's profoundly meaningful. For a brief moment in cosmic time, beings on a small planet managed to detect and measure a galaxy a billion light years away, to understand something about its nature, to appreciate its vastness. We reached across the void with our instruments and our mathematics and our curiosity, and we found something magnificent. We made contact, in a sense, with one of the most extreme structures in the universe. That matters. Maybe not to the universe as a whole, Maybe not in any objective cosmic sense, but to us. It matters that we looked. It matters that we wondered. It matters that we cared enough to build telescopes and conduct surveys and analyze data and slowly piece together the story of IC 1101, to dedicate our time and intelligence and resources to understanding something that has no practical impact on our daily lives. And now you know that story. You know that the Milky Way, for all its majesty, for all its hundreds of billions of stars and its 100,000 light-years of span, is small compared to the true giants of the cosmos. You know that IC 1101 contains 100 trillion stars, spans millions of light-years, sits at the heart of a massive galaxy cluster, grew through countless mergers over billions of years. You know that it represents one of the most massive structures in the known universe, a monument to the power of gravity and time. You know this, and in knowing it, you're connected to something larger than yourself, something ancient and vast and strange. You're part of a tradition of human curiosity that stretches back to the first person who looked up at the night sky and wondered what those points of light were, what they meant, how far away they might be. You're participating in the ongoing project of understanding the universe, even if only as an audience member, even if only by listening and learning and allowing yourself to feel wonder. And wonder is enough. You don't need to become an astronomer to appreciate IC 1101. You don't need to memorize its exact dimensions, or calculate its mass, or understand the detailed physics of galactic mergers. You don't need to comprehend every detail to benefit from knowing about it. All you need is the willingness to look up, to ask questions, to feel that mixture of awe and humility that comes from contemplating something vast and ancient and beautiful. All you need is the willingness to let yourself feel small in the best way possible, to recognize that you're part of something much larger than your individual concerns, that the universe extends far beyond your immediate experience, that there are wonders out there that exceed your ability to fully comprehend, but that nevertheless enrich your life simply by existing and by being known.
IC 1101 will still be there tomorrow, glowing softly at the center of Abell 2029, its light continuing its billion-year journey toward Earth, some of it arriving at our telescopes, some of it passing by into the void beyond. New telescopes will observe it with better resolution and sensitivity. New data will be collected, new measurements made, new insights gained. The story will continue, the understanding will deepen, the mystery will unfold further.
And maybe, on some distant world orbiting one of IC 1101's 100 trillion stars, some other form of life is looking up at their own night sky right now, seeing our Milky Way as we see their galaxy, tiny and distant and faint, barely visible, and wondering what exists out there in the cosmic darkness. Maybe they're feeling the same wonder we feel, asking the same questions, seeking the same understanding. We'll probably never know. The distances are too vast, the timescales too long, the practical challenges of interstellar or intergalactic communication too severe. But the possibility itself is beautiful, is meaningful. The idea that consciousness might have emerged elsewhere, that wonder might be a universal response to the cosmos, that somewhere in IC 1101, or in the Milky Way, or in some other galaxy entirely, beings might be looking up and asking why. That idea connects us to something profound, something that transcends our particular species and planet and moment in history. You're part of that connection. You're part of the universe asking questions about itself. And in asking those questions, in seeking understanding, in allowing yourself to feel wonder, you're fulfilling something essential to what it means to be human, to be conscious, to be alive in this particular moment of cosmic history, when our species has the tools to observe galaxies billions of light years away. The Milky Way is home. It always will be. It's where we evolved, where we live, where all of human experience has unfolded. But IC 1101 reminds us that home is just one place among countless others, that our galaxy is one island in an ocean of galaxies, that the universe is vaster and stranger and more wonderful than our ancestors ever imagined, than even we, with all our instruments and theories, can fully comprehend. And that's okay. That's more than okay. That's magnificent. That's exactly as it should be. The universe should exceed our understanding. It should be larger than our ability to fully grasp. It should contain mysteries that challenge us, wonders that inspire us, scales that humble us. Because in that vastness, in that strangeness, in that beautiful incomprehensibility, there's room for meaning, for wonder, for continued discovery, for the ongoing human project of understanding our place in the cosmos. Thank you for spending this time with Infinite Science. Thank you for listening to this story about IC 1101, about the largest known galaxy, about cosmic scale and human curiosity, and the wonder that comes from contemplating our place in the universe. Thank you for allowing yourself to feel that mixture of awe and humility that comes from knowing about something so vast. The universe is vast beyond measure, ancient beyond easy comprehension, strange beyond our ability to fully understand. But you're here, now, aware of it, thinking about it, connected to it through billions of years of cosmic evolution, and through the light of distant galaxies that has traveled across space to reach you. And in this moment, that connection is enough. It's more than enough. It's everything. Keep looking up, keep wondering, keep asking questions, keep allowing yourself to feel small in the best way possible. Keep seeking to understand, even when full understanding seems impossible. Keep marveling at the fact that you are a conscious being in a vast cosmos, that you're made of stardust, that you're the universe experiencing itself.
The cosmos has infinite stories to tell, and we've only just begun listening. IC 1101 is one chapter in that infinite story, one wonder among countless others, one galaxy among trillions. But it's our chapter now, our discovery, our connection to the vast and ancient universe in which we find ourselves.
Until next time, this has been Infinite Science. Thank you for exploring the universe with us. Thank you for wondering. Thank you for being here. The journey continues. The universe awaits. And somewhere out there, across billions of light years of space, IC 1101 continues its slow, ancient dance, gathering galaxies, adding to its mass, dominating its corner of the cosmos, a monument to time and gravity and the magnificent complexity that emerges when the universe has billions of years to build structures from the simplest ingredients. Go forth with wonder. Carry this knowledge with you, and remember that you're part of something larger, something ancient, something beautiful beyond words.